What does a message in a bottle look like when the ocean is the space between stars? Does it look like a radio wave, beaming out a clear signal across the cosmic dark? Or does it look like something far more subtle, a silent, tumbling shard of rock and metal, sent on a journey of millions of years, briefly passing our firelight before disappearing back into the vast, echoing blackness? In 2017, we may have seen one, and we let it get away. For generations, we've scanned the skies, ears perked, hoping to catch the faintest whisper from another civilization. We built colossal dishes, listening for patterns, for mathematical sequences, for anything that screamed intelligence. We imagined grand, unmistakable signals, something designed to be found. But what if the universe doesn't send telegrams? What if it sends riddles? What if the first whisper wasn't a sound at all, but a fleeting shadow, a cosmic anomaly that slipped through our solar system so fast, so strange, that by the time we even grasped what it was already gone? In the autumn of 2017, something utterly unprecedented happened. An object, unlike anything we had ever witnessed, shot through our cosmic neighborhood. It wasn't one of ours. It didn't belong to our sun or our planets or our asteroid belts. It was a visitor, an absolute stranger from beyond the stars. Its official designation is Oumuamua, and to this day, it remains one of the most profound, bewildering mysteries in all of astronomy. Think about that for a moment. Our first confirmed interstellar object, our very first interstellar visitor. And it wasn't just from another star system. It behaved like nothing we'd ever seen in our own. It was shaped so bizarrely, tumbled through space so erratically, and accelerated with such an invisible push that the scientific community has been locked in a fierce, often passionate, debate ever since. Was it a new, never-before-imagined type of natural celestial body? Or was it, as some daring minds suggest, the first credible evidence of an extraterrestrial technology? A piece of cosmic flotsam, perhaps, from a civilization we can barely imagine. The story of Oumuamua begins not with grand pronouncements, but with a quiet, diligent observation on a Hawaiian mountaintop. It was October 19, 2017, and Canadian astronomer Robert Weirich was sifting through data from the Pan-STARRS 1 telescope, perched on the summit of Haleakala, Maui. This wasn't a telescope designed for interstellar tourism. It was part of NASA's Planetary Defense Coordination Office, built to scan the skies for near-Earth objects, the asteroids and comets that might pose a threat to our planet. It was a cosmic neighborhood watch, looking for familiar faces, but that night, Weirich found something that was anything but familiar. He spotted a faint, fast-moving speck, a tiny pixel of light against the infinite canvas of space. Its trajectory was immediately alarming, but not in the way you might think for a planetary defense system. This object wasn't on a path to collide with Earth. Its path was far stranger. It was on what astronomers call a hyperbolic trajectory. Imagine throwing a ball so hard it escapes Earth's gravity, never to return. Now imagine that ball wasn't thrown from Earth at all, but from another star system, coming in so fast that our sun's gravity couldn't capture it. Its orbital eccentricity, a measure of how unbound an object is, clocked in at an astonishing 1.8, the highest ever observed at the time. This wasn't just leaving, it was passing through. The implications were immediate and electrifying. This wasn't a comet from the Oort cloud, our solar system's icy frontier. This wasn't an asteroid from the main belt. This was an interloper, an immigrant from another star, soaring into our system for the very first time. Robert Weirich had just made history. He had discovered the first confirmed interstellar object ever detected passing through our solar system. But here's where the ticking clock began. The first agonizing twist in this cosmic detective story. When Warwick found Oumuamua, it wasn't arriving, it was leaving. It had already made its closest approach to the Sun, its perihelion, on September 9, 2017, a full 40 days before its discovery. It had swung around our star, getting closer than Mercury's orbit, a mere 0.255 astronomical units away, or roughly 38.1 million kilometers. At that point, it had reached a blistering maximum speed of 87.71 kilometers per second, nearly 196,000 miles per hour. By October 19th, when we finally spotted it, it was already hurtling away at an incredible velocity, having already passed its closest approach to Earth just 5 days prior at approximately 24 million kilometers. A frantic scramble ensued. The astronomical community went into overdrive. Every available telescope on Earth and in space swiveled to get a look at this unprecedented visitor. Teams of scientists, led by figures like Dr. Karen Meach at the University of Hawaii, raced against time. From the Very Large Telescope in Chile to Gemini South, Keck 2, and even the Hubble and Spitzer space telescopes, every lens became an eye, straining to capture data before this fleeting phantom vanished forever. They knew they had only a precious few weeks, maybe a couple of months, before it became too faint for even the most powerful instruments to see. In the end, Oumuamua was tracked for about 80 days after its discovery before it disappeared into the interstellar void. This wasn't just a scientific observation. It was a desperate attempt to gather crumbs of information from a leaving guest. It was like finally spotting a message in a bottle floating by, only to realize it's already far out to sea, and you have no boat, no means to reach it, only binoculars to squint at its receding form. The object was initially classified as a comet due to its hyperbolic trajectory, then reclassified as an asteroid when no cometary tail was observed. Finally, it was given the unique designation 1I for the first interstellar object. Its name, Oumuamua, was chosen by the Pawn Stars Discovery Team, and it's Hawaiian for a messenger from afar arriving first, or scout. Imagine the excitement, the awe, the sheer terror of that moment. For decades, the existence of interstellar objects had been purely theoretical, a whispered possibility in the halls of astrophysics. And then, suddenly, there it was, not a theory, but a tangible physical reality, a piece of another star system right here in our cosmic backyard. And we almost missed it entirely. The discovery was a cosmic wake-up call, a dramatic realization that the universe is far more dynamic and surprising than we often give it credit for. Before Oumuamua, the idea of an object from another star system passing through ours was a compelling theoretical concept, but it lacked the undeniable punch of empirical evidence. Then, on that fateful October night, Robert Warwick saw it, and the theoretical became terrifyingly, wonderfully real. It confirmed that our solar system isn't hermetically sealed. It's permeable, a cosmic port of call for travelers from the deep, dark ocean of interstellar space. The scientific community, as you can imagine, went into a kind of controlled chaos. This wasn't just a new comet or asteroid. This was a whole new class of object. It demanded immediate, intense scrutiny. Every available instrument, every pair of expert eyes, focused on that rapidly fading speck. Astronomers like Dr. Karen Meach, who led an international team, worked around the clock, grappling with the profound limitations of observing something that was already a quarter of the way out the door. They were trying to characterize its properties, its size, its shape, its color, its rotation, all while it sped away at tens of thousands of miles per hour, getting fainter with every passing moment. And what they saw, even with the limited data they could collect, only deepened the mystery. Oumuamua, exhibited a reddish color, similar to many objects found in the outer solar system, suggesting it had been exposed to cosmic rays for millions of years. It was observed to be tumbling chaotically on a non-principal axis rotation, rather than spinning smoothly, which further added to its strange profile. But these were just the appetizers to the truly bizarre main course. The tragedy, the true aha moment that still reverberates through the scientific community, is the realization that our first potential interstellar message wasn't a carefully crafted radio wave. It wasn't a beacon. It was a physical object, a silent traveler. And we were caught entirely unprepared. We had no rapid response missions, no interceptors. We could only watch, measure, and wonder as it continued its silent, lonely journey back into the dark. And the more we watched, the more we measured, the stranger Oumuamua became. Because beyond its unprecedented origin, beyond the drama of its fleeting visit, lay a series of anomalies that defied every known explanation. Anomalies so profound, so baffling, that they would force scientists to consider possibilities previously relegated to the realm of science fiction. Its shape, its behavior, its very essence, everything about it screamed unprecedented. And it demanded an explanation. This wasn't just a scientific curiosity. It was a profound philosophical challenge. It forced us to confront our assumptions about what extraterrestrial intelligence might look like, or indeed, what any interstellar object might look like. We've been conditioned by decades of science fiction to imagine aliens as green men or sleek spaceships. But what if the truth is far more subtle, far more prosaic, yet infinitely more profound? What if, when a message in a bottle crosses the vast cosmic ocean, it looks less like a triumphant signal and more like a silent, tumbling shard, a piece of something broken, or perhaps a deliberately inert probe, simply observing? The fact that we missed its arrival, that we only caught a glimpse of it on its way out, amplifies the sense of lost opportunity, the poignant question of, what if? Had we been watching just a little sooner? Had our telescopes been pointed in just the right direction? Had we had the technology to intercept it? What might we have learned? The very notion that this silent visitor could be artificial, a piece of technology from another civilization, elevates the Oumuamua mystery from a mere astronomical puzzle to one of humanity's most high-stakes scientific detective stories. It's a real unsolved mystery, brimming with all the elements of great science fiction, yet grounded in the indisputable facts of astronomical observation. This is not a retrospective on a solved case. It's an active, ongoing scientific debate with paradigm-shifting implications. We, as an audience, are invited to weigh the evidence alongside the world's top scientists, to join the two tribes in their clash of brilliant minds and bold ideas. The emotional and philosophical depth of this story is immense, tapping into our deepest human emotions of loneliness, curiosity, and the relentless search for meaning in the cosmos. It forces us to ask, are we alone? And if not, how would we ever know? The sheer fleetingness of Oumuamua's visit is a central part of its enigma. It hurtled through our system, around our sun, and then out again, never to return. Its hyperbolic excess velocity of 26.33 kilometers per second at entry, about 59,000 miles per hour, meant it was never going to be gravitationally bound to our sun. It was always just passing through, a cosmic tourist on an unfathomably long journey. The very speed and trajectory confirmed its interstellar origin beyond any doubt. But that same speed and trajectory also ensured that our chance to study it was agonizingly brief. So, as Oumuamua faded from our view, disappearing back into the cold, dark ocean between stars, it left behind not answers, but questions. Deep, unsettling, paradigm-shifting questions. Questions about its extreme cigar-like shape, or perhaps a flat, pancake-like shape, depending on the interpretation of its light curve data. Questions about its startling lack of a cometary tail or coma, despite its behavior. And most importantly, questions about its non-gravitational acceleration. The subtle, inexplicable push it experienced as it moved away from the sun, with no visible means of propulsion. This was the core visual mystery, the deviation from the path predicted purely by gravity. A tiny but statistically significant velocity change of about 17 meters per second, detected at a staggering 30 sigma significance. Something was pushing Oumuamua, and we couldn't see what it was. These anomalies, these profound deviations from what we expect of natural objects, are what ignited the fierce debate that continues to this day. They are the strange evidence that compels us to look beyond the ordinary, to consider the extraordinary. What exactly was this silent, tumbling shard that briefly passed our firelight? And what does its fleeting visit tell us about our place in a universe that is far stranger and perhaps far more populated than we ever dared to imagine? And what does its fleeting visit tell us about our place in a universe that is far stranger and perhaps far more populated than we ever dared to imagine? Imagine for a moment the vast, silent ocean between stars. Billions of miles of absolute nothing, stretching out further than our minds can truly grasp. Now, picture a message in a bottle, tossed from some distant, unseen shore, drifting for epochs, finally catching a current that brings it, by pure chance, toward our own little island. You spot it, just as it's about to be swept away, forever lost to the dark. That's precisely the cosmic detective story that unfolded in 2017. A high-stakes race against time to observe the most crucial clue we'd ever encountered, spotted just as it was about to disappear into the interstellar tide. The year was 2017. The place, a serene mountaintop in Hawaii, home to the Pan-STARRS 1 telescope. This isn't just any telescope. It's a vigilant sentinel, funded by NASA's Planetary Defense Coordination Office, constantly sweeping the night sky for near-Earth objects, asteroids and comets that might pose a threat. It's a crucial job at keeping an eye on our cosmic neighborhood, making sure nothing unexpected is hurtling our way. On October 19, 2017, a Canadian postdoctoral researcher named Robert Warwick was sifting through the data captured by this tireless guardian. He wasn't looking for alien spacecraft. He was looking for routine garden-variety rocks. But what he found was anything but routine. Warwick noticed a faint, fast-moving speck of light, a blip in the data that didn't quite fit the profile of anything Pan-STARRS had seen before. It was moving too quickly, on a trajectory that was, to put it mildly, unusual. As astronomers plotted its course, their excitement, and perhaps a touch of apprehension, began to build. This object wasn't orbiting our sun. It wasn't looping around like the familiar comets and asteroids that call our solar system home. No. This object was on a hyperbolic trajectory, meaning its path was so elongated, so stretched out, that it would slingshot around our star once and then, with incredible speed, escape its gravitational embrace forever. Its orbital eccentricity was calculated at 120, the highest ever observed at the time, a clear mathematical declaration that this visitor was not from around here. It was, in fact, the first confirmed interstellar object ever detected passing through our solar system. Think about that for a moment. For decades, scientists had theorized about the existence of such wanderers, objects ejected from other star systems, drifting through the galactic void. But until this moment, they were just theoretical. Now, one was here, right in our cosmic backyard, and the frantic, high-stakes race against time had begun. The initial classification of this enigmatic visitor was a comedy of scientific errors, or perhaps a testament to its unprecedented nature. It was first labeled a comet, CU 2017 U1, because its hyperbolic trajectory hinted at an origin beyond our sun's gravitational pull, a characteristic often associated with comets. But then, a critical detail emerged. It lacked a coma, that fuzzy envelope of gas and dust that typically surrounds an active comet. No visible tail, no telltale signs of outgassing. So, it was reclassified as an asteroid, EA 2017 U1. But even that didn't feel quite right. It was too fast, too strange. Finally, it received its own unique designation, a recognition of its singular status, 1I 2017 U1, or simply 1I. The I stood for interstellar, marking it as the first of its kind. The name chosen for it, by the Pan-STARRS Discovery team based in Hawaii, was Oumuamua, a beautiful Hawaiian word, meaning a messenger from afar, arriving first, or scout. A truly fitting name for such a profound visitor. But here's where the tragedy of the one that got away truly begins to sink in. When Robert Varick spotted Oumuamua on October 19, 2017, it wasn't just passing through, it was already leaving. It had already made its closest approach to the sun. Its perihelion on September 9, 2017, just over a month before its discovery. It had also zipped past Earth at its closest approach on October 14, 2017, only 5 days before its detection. By the time we knew it was here, Oumuamua was already hurtling away from us, out of our solar system, gaining incredible speed. It had entered our cosmic neighborhood with a hyperbolic excess velocity of about 26.33 kilometers per second, nearly 59,000 miles per hour, and accelerated to a maximum speed of 87.71 kilometers per second, or a breathtaking 196,000 miles per hour, at its perihelion. This was no leisurely stroll. This was a bullet train through our system, and we only saw the exhaust fumes. The astronomical community exploded into a frenzy. Every available telescope on Earth and in space swiveled to get a look. This was an unprecedented opportunity, a chance to study an object from beyond our wildest dreams. The Very Large Telescope, Gemini South, Keck 2, the Hubble Space Telescope, even the Spitzer Space Telescope, all turned their powerful eyes toward the faint, receding speck. Astronomers like Dr. Karen Meach at the University of Hawaii's Institute for Astronomy, who led an international team, worked tirelessly, desperate to gather as much data as possible before our fleeting visitor vanished entirely. They were racing against a clock that was ticking down at an unforgiving pace. The aha moment of this story, the moment that makes it so compelling and so heartbreaking, is just how limited that window truly was. We only had a few weeks. Roughly 80 days after its discovery, Oumuamua became too faint, too distant, too fast for even the most powerful telescopes to observe. It was like trying to study a rare, exotic bird as it flashes past your window at 200 miles an hour. You catch a glimpse, maybe a few blurred details, and then it's gone, leaving you with more questions than answers. The scarcity of time is what makes the mystery of Oumuamua not just compelling, but also deeply tragic. We had a chance, a brief, fleeting moment, to glimpse something truly extraordinary, a potential message in a bottle from the stars, and we barely got to read the label before it slipped back into the cosmic currents. Imagine the frustration, the intellectual agony of those astronomers, knowing they were witnessing a once-in-a-humanity event, but with their hands tied by the laws of physics and the limitations of discovery. Every single data point was precious, painstakingly extracted from the faint light of an object that seemed to be actively trying to evade our gaze. The data they did manage to collect, however, was astonishing, fueling the very anomalies we discussed. Its brightness, for example, varied dramatically, by a factor of 10, as it tumbled chaotically on a non-principal axis rotation, rather than spinning smoothly like most astronomical bodies. This extreme variation strongly suggested a highly elongated shape, unlike any known asteroid or comet in our solar system. Early estimates described it as cigar-like, perhaps 10 times longer than it was wide. Later analysis, however, also entertained the possibility of a flat, pancake, or oblate spheroid shape. Whether a cosmic cigar or a flat disk, it was a shape that screamed unfamiliar. It also exhibited a reddish color, similar to many objects found in the outer solar system, hinting at a composition of rock and possibly metals, having been exposed to cosmic rays for millions of years. This frantic scramble, this desperate attempt to understand our first interstellar visitor, was more than just scientific curiosity. It was a profound encounter, a moment that forced us to confront the possibility that the universe is not just vast, but also brimming with things we can barely conceive. The fact that we missed our chance to study it properly, that we let it get away, became a wake-up call for the entire scientific community. The experience of Oumuamua highlighted the urgent need for faster detection systems and rapid response capabilities. Projects like the Vera C. Rubin Observatory, currently under construction, are now being designed with the explicit goal of detecting interstellar objects more frequently, perhaps even once a year, giving us a better chance to prepare for the next messenger from afar. But for Oumuamua, the opportunity was lost. It continues its silent, solitary journey, accelerating away from our sun at an incredible clip, destined to disappear into the interstellar void from which it came. Its brief passage left us with a tantalizing glimpse of the unknown, a cosmic riddle whispered on the stellar winds. What exactly was it? A new type of natural phenomenon, or something far more profound? The questions linger, echoing in the vast silence it left behind. And in that lingering mystery lies the profound lesson of Oumuamua. Sometimes, the most important messages are the ones we almost miss, the ones that force us to look closer, to question everything we thought we knew, and to prepare ourselves for the next time the universe decides to send us a scout. But for Oumuamua, the opportunity was lost. It continues its silent, solitary journey, accelerating away from our sun at an incredible clip, destined to disappear into the interstellar void from which it came. Its brief passage left us with a tantalizing glimpse of the unknown, a cosmic riddle whispered on the stellar winds. What exactly was it? A new type of natural phenomenon, or something far more profound? The questions linger, echoing in the vast silence it left behind. And in that lingering mystery lies the profound lesson of Oumuamua. Sometimes, the most important messages are the ones we almost miss, the ones that force us to look closer, to question everything we thought we knew, and to prepare ourselves for the next time the universe decides to send us a scout. The universe, you see, operates on rules. Rules that we, as humans, have painstakingly deciphered over centuries, piece by intricate piece. Gravity, for instance, is one of the grand maestros of the cosmos, orchestrating the dance of planets around stars and stars around galaxies. When an object, like a comet or an asteroid, enters our solar system, we can predict its path with breathtaking precision. It's like watching a master craftsman at work, every movement logical, every outcome predetermined by the forces at play. So, when Oumuamua shot through our cosmic neighborhood in 2017, astronomers immediately began to chart its course. They fed the initial observations from the Pan-STARRS telescope into their sophisticated models, expecting to see a trajectory dictated purely by the sun's gravitational pull. And for a while, it seemed to follow the script. It was moving fast, incredibly fast, with an orbital eccentricity of 1.20, which is the highest ever observed. That number, above 1.0, was the undeniable mathematical proof that this wasn't just another space rock orbiting our sun. This was an interloper, a genuine interstellar traveler from beyond our stellar homes. It had entered our solar system with a staggering hyperbolic excess velocity of 26.33 kilometers per second. That's nearly 60,000 miles per hour, and would reach a maximum speed of nearly 88 kilometers per second at its closest approach to the sun. It was a celestial cannonball, screaming through the void. But then, something started to go wrong with the predictions. Not wrong in a catastrophic, end-of-the-world kind of way, but wrong in a subtle, deeply unsettling scientific sense. Imagine for a moment, you're standing on the shore, watching a speedboat zip across the water. You can see the boat, you can hear its engine, and you can clearly see the wake it leaves behind. From that wake, you can easily predict its next move, its trajectory. Now, imagine a different scenario. You see a wake, a perfectly ordinary wake, but there's no visible boat. Yet, the wake itself is moving, not just drifting, but actively accelerating, as if an invisible engine is pushing it forward, defying every expectation. That, in essence, is the core of the Oumuamua mystery. As astronomers continued to refine their calculations, poring over the precious few weeks of data they managed to snatch, they noticed a tiny, yet statistically significant deviation. Oumuamua wasn't just following the sun's gravity. It was accelerating ever so slightly as it moved away. Not a massive burst of speed, not some dramatic, fiery propulsion, but a gentle, persistent push. It was as if an unseen force was nudging it along, causing its actual path to diverge from the one predicted by gravity alone. This wasn't a minor rounding error. This was a fundamental challenge to the very physics they understood. The deviation was detected with an astonishing 30 sigma significance, meaning the chances of it being a random fluctuation were practically zero. Over its observed trajectory, this invisible push added up to a total velocity change of approximately 17 meters per second. 17 meters per second might not sound like much when you're talking about an object traveling at hundreds of thousands of miles an hour, but in the realm of celestial mechanics, it was a thunderclap. This deviation was the aha moment, the point where the scientific community collectively realized they were looking at something truly unprecedented. We can visualize this divergence perfectly. Picture a line, clean and elegant, representing the path Oumuamua should have taken, had it been solely under the influence of the sun's gravity. It's a graceful curve, a perfect arc. Now picture a second line, overlaid on the first, but subtly, undeniably pulling away. As Oumuamua reached its closest point to the sun, its perihelion, on September 9, 2017, at a mere 0.035 AU, closer than Mercury's orbit, and then began its outward journey. On that second line, its actual observed path started to drift, just a little at first, then more definitively, pushing away from the gravitational prediction, as if gently propelled by an invisible hand. It was a cosmic wrong turn that nobody could explain. Now, you might be thinking, well, that's simple. It's just a comet. Comets do that all the time. And you'd be right, in principle. Comets are famously non-gravitational. As they approach the sun, the ice and dust on their surface heat up, sublimate, and are ejected into space, forming that iconic glowing coma and tail. This outgassing acts like tiny thrusters, giving the comet a gentle push, causing it to deviate from a purely gravitational path. It's a well-understood phenomenon. But here's the rub, the profound head-scratching paradox of Oumuamua. There was no tail, no visible coma, nothing. The frantic observation campaign, involving every major telescope on Earth and in space, from the Very Large Telescope to Hubble and Spitzer, all raced against the clock, trying to get a good look before it vanished. They looked for the telltale signs of cometary activity, for the faint, fuzzy glow of gas and dust. They looked for the spectral signatures of water vapor, carbon dioxide, or any other volatile compounds. They looked and they looked, and they found nothing. The object remained stubbornly, eerily silent, a stark, dark silhouette against the backdrop of space. Karen Meach, an astronomer at the University of Hawaii, who led an international team characterizing Oumuamua, noted its extreme brightness variations and reddish color, but no sign of a coma. It was initially classified as a comet due to its hyperbolic trajectory, then reclassified as an asteroid when no coma was observed, before finally earning its unique designation as the first interstellar object, one eye. Adding to this perplexing profile was its bizarre appearance. While we don't have direct images, the way its brightness dramatically changed as it tumbled, by a factor of 10, told astronomers that it had an extreme shape. Initial models suggested a highly elongated cigar-like object, perhaps 10 times longer than it was wide, unlike any known asteroid or comet in our solar system. Later analysis even suggested it might be a flat, pancake, or oblate spheroid shape. And it wasn't spinning smoothly, but rather tumbling chaotically on a non-principal axis rotation, further adding to its alien profile. This strange, silent, accelerating, tumbling shard of rock and metal was a puzzle wrapped in an enigma, hurled into our solar system from across the vast, dark ocean between stars. Robert Varick, the Canadian astronomer who first spotted Oumuamua in Pawn Stars data, expressed his skepticism about anything beyond natural explanations, but even he couldn't deny the anomalies. The scientific community was in a frenzy. This wasn't just another discovery. This was a fundamental challenge to their understanding of celestial mechanics. They had only a precious 80-day window after discovery before it became too faint to observe, a frantic, ticking clock race to gather as much data as possible. Every telescope, every instrument, every pair of eyes that could be brought to bear was focused on this one, fleeting visitor. The data was meticulously collected, analyzed, and reanalyzed. The numbers didn't lie. The acceleration was real. The silence was real. The stage was set for a scientific debate unlike any other. How do you explain an object that behaves like a comet, but shows no visible signs of being one? An object whose very existence seemed to whisper of forces unknown, or perhaps technologies unimagined. The universe had sent us a message, but it was written in a language we barely understood, a silent defiance of our most cherished laws of physics. And, as Oumuamua continued its lonely journey back into the interstellar void, it left behind not just a mystery, but a profound question that continues to echo in the halls of science. What exactly was that invisible engine? And what does its silent, accelerating departure truly mean for our understanding of the cosmos? The invisible engine was one thing, a profound puzzle of physics, a silent defiance of our most cherished laws. But what about the driver of that engine? What did this silent traveler, this messenger from afar, even look like? This was another layer of the mystery, one that forced astronomers to become cosmic detectives, piecing together a portrait from the faintest, most fleeting clues. Imagine for a moment You are a lighthouse keeper. Night after night, you watch the ships pass on the distant horizon, their lights blinking in the dark. Most ships, you know, have steady lights, or perhaps they dim and brighten gently as they turn in the vast ocean. You can't see the ship itself, not really, just that distant glimmer. But then one night, a new light appears. It blinks, not just a gentle dimming, but a dramatic, almost frantic surge, from barely visible to blindingly bright, then back to almost nothing. It does this over and over again, in a rhythmic, repeating pattern. Without ever seeing the ship, you'd know, wouldn't you? You'd know that ship wasn't shaped like any other you'd ever seen. It must be long and thin, or maybe incredibly flat, tumbling end over end, presenting sometimes its broad face, sometimes just its razor-thin edge to your gaze. That wildly flickering light, that dramatic variation, would be your only clue to its utterly bizarre form. That, my friends, is almost exactly what happened with Oumuamua. It was a glimmer in the dark, a distant, tumbling shard of rock and metal, sending us a peculiar signal about its very essence. When Pawn Stars first caught sight of it, on October 19th, 2017, it was already well on its way out, a tiny pinprick of light against the vast canvas of space. It was moving at an astounding clip, having already zipped past the sun a month earlier on September 9th, where it reached a blistering speed of nearly 196,000 miles per hour. By the time our telescopes really got a bead on it, Oumuamua was already approximately 24 million kilometers from Earth. It wasn't just far away. It was tiny, estimated to be at most a quarter-mile long, or about 400 meters. To get a clear picture of something that small, that fast, and that distant, well, it's like trying to photograph a housefly buzzing across the country at night with a telescope. You just can't do it. There are no direct, crisp images of a Oumuamua. Only that glimmer, that changing light. But that glimmer, that light curve, held secrets. Astronomers, led by Dr. Karen Meach at the University of Hawaii's Institute for Astronomy, were able to track Oumuamua's brightness as it moved through the sky. What they found was astonishing. The light from Oumuamua didn't just dim a little. It varied wildly by a factor of 10. Think about that. At its brightest, it was 10 times brighter than at its dimmest. This wasn't a gentle sway. This was a disco ball in space, flashing its presence with dramatic flair. To understand why this is so profound, let's go back to our lighthouse keeper. If a ship's light dims by a tiny fraction, it might just be the ship turning slightly, or perhaps a cloud passing. But if it dims by 10 times, it means that at one point, you're seeing a huge reflective surface, and at another, you're seeing almost nothing at all. For an object in space, this means its shape must be incredibly extreme, and it must be tumbling or rotating in a very specific way. Most asteroids and comets we see in our own solar system are, to put it mildly, lumpy potatoes. They might be a bit elongated, maybe twice as long as they are wide, but nothing like what Oumuamua's light curve was telling us. When astronomers crunched the numbers, that factor of 10 variation in brightness pointed to an object with an aspect ratio of at least 10.1, 10 times longer than it was wide. This was the aha moment, the realization that we were dealing with something completely unprecedented. It was a cosmic anomaly, a data point that refused to fit neatly into any existing box. So, what does an object with a 10.1 aspect ratio look like? Well, there were two main candidates that emerged from the data, two shapes that could produce such a dramatic light curve as they tumbled. One possibility was a long, thin cigar-like object, perhaps 400 meters long, but only 40 meters wide. Imagine a cosmic pencil, spinning end over end as it hurtled through space. When you see it face on, its broad side reflects a lot of sunlight, making it bright. But as it tumbles and you catch it edge on, almost no light reflects back, and it dims dramatically. This was the initial most popular mental image of Oumuamua, a cosmic cigar. It invoked a sense of sleekness, of purpose, perhaps even a sense of design. The other, equally bizarre possibility was that it wasn't a cigar at all, but a very flat, pancake-like or oblate spheroid shape. Think of it like a cosmic dinner plate, or perhaps a shard of something much larger, incredibly wide but razor-thin. If this flat object were tumbling, presenting its broad face to us, it would be incredibly bright. But as it rotated to show us its narrow edge, it would virtually disappear. This interpretation also fit the extreme brightness variations perfectly. It was a shape that whispered of vast, thin surfaces, perhaps designed to interact with the subtle pressures of starlight. Here's the kicker, the part that truly rattled the scientific community. Whether it was a cigar or a pancake, neither shape is common or even remotely typical for natural objects in our solar system. Asteroids and comets typically form through accretion, slowly gathering material, which tends to result in more irregular, but generally more compact, shapes. They don't naturally sculpt themselves into perfect, extreme needles or impossibly thin wafers. Our solar system is full of cosmic rubble, but it's mostly lumpy potato-shaped rubble, not geometrically extreme forms. Furthermore, the light curve also revealed that Oumuamua wasn't just spinning smoothly like a top. It was observed to be tumbling chaotically, in what scientists call a non-principal axis rotation. Instead of a stable, predictable spin around a single axis, it was wobbling, precessing, and rotating around multiple axes at once. It was performing a complex cosmic ballet of disorientation, like a poorly thrown football, spiraling unpredictably. This chaotic tumble further amplified the dramatic swings in brightness, making it even harder to precisely pin down its exact dimensions, but reinforcing the notion of an utterly alien geometry and behavior. This wasn't just an odd shape, it was an odd shape behaving oddly. This extreme shape, deduced purely from the simple act of measuring how much light it reflected, was yet another flag raised on the Oumuamua mystery. It joined the non-gravitational acceleration and the lack of a visible coma in forming a trio of anomalies that defied easy explanation. If it was a natural object, what incredible forces could have sculpted it into such an extreme form? How could it have survived an interstellar journey of millions of years without being battered into something more mundane, something more like the familiar space rocks we've come to expect? The universe is a violent place, and such delicate, extreme forms are rarely preserved over cosmic timescales. And this is where the profound implications truly begin to sink in. Because if you accept the premise that natural processes tend to create objects with a certain range of shapes, your lumpy potatoes, your slightly elongated pebbles, then an object that deviates so wildly demands a deeper look. It forces you to ask, what if the forces at play weren't purely natural? What if, like our lighthouse keeper, inferring the strange ship from its peculiar light, we were seeing the deliberate design of something artificial? This wasn't just a scientific curiosity. It was a philosophical provocation, challenging our deepest assumptions about the cosmos. The cigar-like shape you initially invoked images of interstellar spaceships from science fiction, sleek and aerodynamic, built for journeys across the void. The pancake shape, while less visually familiar from sci-fi, opened up equally intriguing possibilities, such as a light sail, a vast, ultra-thin sheet designed to be propelled by the pressure of starlight, a concept we'll delve into deeper later. Both shapes, in their extreme nature, challenged our preconceived notions of what a wanderer from another star system should look like. They suggested a level of engineering, whether natural or artificial, that was simply beyond our current understanding. Dr. Karen Meach, whose team was instrumental in characterizing Oumuamua, noted these extreme brightness variations as a defining characteristic. This wasn't some minor detail. It was a screaming siren from the data, telling us this object was fundamentally different. The fact that it was tumbling, rather than smoothly rotating, added another layer of complexity and peculiarity. It wasn't just oddly shaped, it was behaving oddly too. This compounded the strangeness, making it harder to fit into any known category of celestial objects. So, while we couldn't gaze upon Oumuamua with our own eyes, we could, through the sophisticated language of light, discern its ghostly outline. We knew it was long, or it was flat. We knew it was tumbling. And we knew with absolute certainty that we had never ever seen anything quite like it before in our own cosmic backyard. No asteroid, no comet, no dwarf planet, no moon in our solar system boasts such an extreme aspect ratio of 10:1. This was an outlier in the truest sense of the word, a statistical anomaly so profound that it shattered our expectations and expanded our imagination. It was a cosmic fingerprint, unique and perplexing. The implications of this bizarre shape were enormous, bifurcating the scientific community into two distinct tribes. For the natural origin camp, it meant proposing new exotic formation mechanisms. Perhaps it was a fragment of a Pluto-like exoplanet, chipped off during a cataclysmic collision, and then eroded by interstellar radiation over eons into an impossibly thin sliver. This nitrogen iceberg theory, proposed by Alan Jackson and Stephen Desch, suggested that a chunk of frozen nitrogen, like the surface of Pluto, could have been ejected from a distant planetary system. Over millions of years, as it traveled through the interstellar medium, cosmic rays would have slowly eroded its surface, preferentially shaping it into an extremely thin, flat object. This required a very specific set of circumstances and a rather precise erosion process, but it was a natural explanation, attempting to account for the extreme shape. Another natural hypothesis, the hydrogen iceberg theory by Darrell Seligman and Gregory Laughlin, posited the object was made of solid hydrogen. This also presented a challenge, as hydrogen ice is incredibly fragile and would sublimate very rapidly, even in the cold vacuum of space, making it difficult for such an object to survive an interstellar journey. Yet, if it could survive, its rapid evaporation could also contribute to shaping it into an elongated or flattened form. These theories, while ingenious, pushed the boundaries of our understanding of cosmic geology, requiring us to imagine an interstellar medium capable of carving such precise, extreme forms or planetary systems, producing fragments utterly unlike anything we've observed in our own. They were bold, creative hypotheses, but they also highlighted just how unnatural Oumuamua appeared to be within our existing frameworks. On the other side, for those who dared to entertain the artificial hypothesis, this extreme shape was another compelling piece of the puzzle. An interstellar light sail, for instance, would need to be incredibly thin and wide to maximize its surface area for stellar radiation pressure, much like the pancake shape inferred from the light curve. Such a craft would be designed for interstellar travel, silently propelled by the gentle push of starlight from a distant sun. A long, cigar-shaped object could be a probe, designed for stability and perhaps containing internal components, sleek and durable for a journey spanning millions of years. The very unnaturalness of the shape, from a terrestrial perspective, became an argument for its engineered nature. It was as if the universe had presented us with a perfect aerodynamic profile. But for a medium far different from Earth's atmosphere, the vacuum of space, where aerodynamics takes on an entirely new meaning when driven by light. For proponents of this view, the extreme aspect ratio was seen to challenge to explain. It was an expected feature of an interstellar technology. This glimmer in the dark was more than just data. It was a Rorschach test for our understanding of the universe. Did we see a new exotic branch of natural phenomena pushing the limits of our current models? Or did we see the unmistakable, if silent, signature of intelligence hinting at structures and technologies beyond our wildest dreams? The debate was just beginning, fueled by every strange flicker of light, every inexplicable twitch in its trajectory. It forced us to confront our biases, to question our assumptions, and to consider the truly extraordinary. The astronomers, in their frantic race against time, had managed to capture enough of that flickering light to tell us a story of an object unlike any other, an object that, even without a visible engine, even without a discernible message, shouted its uniqueness through the sheer oddity of its form. And as it faded from view, becoming too faint for even the most powerful telescopes to observe, after only about 80 days, that silent, tumbling shard continued its journey, leaving us not with answers, but with a profound, unsettling wonder. It left us with the image of a cosmic messenger, shaped like a question mark, hurtling back into the interstellar ocean, perhaps carrying secrets we were only just beginning to comprehend. The light from that distant, tumbling shard had revealed its bizarre form, but the true meaning of that form was still utterly lost in the dark. It forced us to ponder, what does it truly mean to be natural when the cosmos itself is capable of such outlandish creations? You see, the cosmic dance is often a predictable one. Gravity, that invisible puppeteer, pulls every star, every planet, every errant rock along its appointed path. And for the most part, it does a pretty good job. When astronomers map an object's trajectory, they can predict its future and even rewind its past with astonishing precision. So when Oumuamua first appeared, hurtling into our solar system from the vast, dark ocean, between stars, scientists did what they always do. They plotted its course. They watched it slingshot around our sun, picking up incredible speed, an astounding 87.71 kilometers per second. At its closest approach, a mind-boggling 196,000 miles per hour. Then, just as expected, it began its long, lonely journey back out, destined to disappear into the interstellar void forever. But as more and more data poured in, from telescopes across the globe, from the Very Large Telescope in Chile to Gemini South, Keck 2, and even the Hubble and Spitzer space telescopes, a strange discrepancy began to emerge. The calculations weren't quite adding up. It was subtle at first, a whisper in the data, but it grew louder with every new observation. Oumuamua wasn't following the path dictated purely by gravity. It was deviating, it was accelerating. Not by much, mind you. A cumulative velocity change of only about 17 meters per second by the time it left our system. But it was there, undeniably. A gentle, persistent push, as if something unseen was nudging it along. This phenomenon, this non-gravitational acceleration, isn't unheard of in the cosmos. In fact, it's the calling card of one of the most beautiful and common objects we know. The comet. Imagine, if you will, an engine roaring to life. You expect to see exhaust fumes, right? A plume of smoke, a trail of fire, some visible evidence of the force propelling it forward. That's what a comet is. A cosmic engine, powered by the sun. As a comet approaches our star, the sun's heat begins to vaporize the ice and dust locked within its nucleus. This gas and dust erupts from the comet's surface, creating that iconic ethereal tail, a luminous coma that can stretch for millions of miles, shimmering against the blackness of space. This outgassing, this stream of vaporized material, acts like tiny thrusters, giving the comet a gentle, continuous push that subtly alters its trajectory, nudging it away from the sun. It's a natural, well-understood form of non-gravitational acceleration, and for a while, that's exactly what astronomers thought Oumuamua was. Its highly eccentric, hyperbolic trajectory, with an orbital eccentricity of 1.4, immediately told them it wasn't from around here. It was an interstellar visitor, unbound by our sun's gravity. And since interstellar objects were theorized to be mostly cometary, it was initially classified as Cibar-like 17U1, a comet. The assumption made sense, but then the telescopes kept watching, and they saw nothing, no tail, no coma, not a whisper of gas, not a speck of dust. From every angle, every wavelength, Oumuamua remained stubbornly, unnervingly silent. It looked, for all intents and purposes, like a naked asteroid, a silent shard of rock, reddish in color, perhaps composed of rock and metals, baked by millions of years of cosmic rays in the lonely dark between stars. But asteroids don't accelerate like that. Asteroids follow gravity's rules to the letter, and this object clearly was not. It was a profound contradiction. You had an object accelerating like a comet, yet looking nothing like one. It was the engine roaring, but with no exhaust fumes. The push was there, undeniably, detected with a statistical significance of 30 sigma, a level of certainty that makes it virtually impossible to be a fluke. But the evidence of its cause was missing. This wasn't just a minor anomaly. It broke one of astronomy's fundamental rules about how things move in space. It shattered the simple, comfortable explanations. Think about it. For decades, scientists had theorized that interstellar objects existed, but Oumuamua was the first confirmed one. And when it finally arrived, it thumbed its nose at our expectations. This strange visitor, already defying conventions with its extreme shape, sometimes described as a cigar-like object 10 times longer than it was wide, other times as a thin, tumbling pancake or oblate spheroid, now presented an even deeper mystery. It was tumbling chaotically on a non-principal axis rotation, adding another layer to its bizarre profile. The implications were staggering. If this wasn't a comet, what was providing the push? If it wasn't an asteroid, what was its composition? The scientific community, already buzzing with the excitement of an interstellar visitor, was now gripped by a frenzy of bewildered curiosity. Every available telescope had been swiveled to get a look, a frantic race against the clock, as the object discovered by Robert Werik at the Pan-STARRS 1 telescope on October 19, 2017, was already heading out of our solar system, having passed its closest point to the Sun just over a month earlier, on September 9, 2017. They had a precious window of about 80 days to gather all the data they could before it became too faint to see. And in that brief window, the mystery only deepened. The very next confirmed interstellar visitor, 2I Borisov, which arrived in 2019, only served to highlight Oumuamua's strangeness. Borisov behaved exactly like a typical comet. It had a visible coma, a distinct tail, and its non-gravitational acceleration was easily explained by the outgassing of water ice, just as predicted. Borisov was the textbook example. Oumuamua, however, was the cosmic outlier, the silent anomaly that refused to conform. This glaring absence of a coma forced astronomers to reconsider everything. It led them to reclassify Oumuamua, first from a comet to an asteroid, O2017 U1. when no coma was observed, and then finally giving it the unique designation 1I for the first interstellar object. They were searching for an explanation, any explanation, that could account for that invisible push. What kind of material, if vaporized by the sun, would produce acceleration without leaving a visible trace? This question sparked a scientific quest for novel natural explanations. Perhaps some proposed Oumuamua was made of something incredibly exotic, something we rarely, if ever, see in our solar system. One idea, put forth by Daryl Seligman and Gregory Laughlin, suggested it might be a hydrogen iceberg, a chunk of solid molecular hydrogen. As it warmed, the hydrogen would sublimate, turning directly from solid to gas, providing the necessary thrust. The beauty of this theory was that molecular hydrogen gas is incredibly difficult to detect, especially from light years away. It would, in essence, be an invisible exhaust, a silent engine. But the hydrogen iceberg theory had its own challenges. Could a fragile iceberg of frozen hydrogen survive a journey of millions of years through the harsh vacuum of interstellar space, constantly bombarded by cosmic radiation, without completely evaporating? Many scientists, including Avi Loeb, argued that it couldn't. The journey would be too long, too destructive. Another compelling hypothesis, the nitrogen iceberg theory, came from astrophysicists Alan Jackson and Stephen Desch. They suggested that Oumuamua was a fragment of solid nitrogen ice chipped off a Pluto-like exoplanet in a distant star system. Imagine a world much like our own Pluto, rich in nitrogen ice, somehow shattered in a cosmic collision. A shard of that world, like a piece of a frozen interstellar snowball, could have been ejected into the void. As it entered our solar system, the sun's heat would cause the nitrogen ice to sublimate, producing that invisible outgassing. Nitrogen gas, like hydrogen, would be extremely difficult to detect, especially given the limited observation time and the object's distance. Furthermore, as it sublimated, the nitrogen ice could have eroded the object into that peculiar, flat, pancake-like shape suggested by some light curve analyses. This theory even offered a plausible explanation for the reddish color, as cosmic radiation would gradually process the nitrogen surface, giving it that characteristic hue. These theories, the hydrogen and nitrogen icebergs, represented desperate but ingenious attempts to keep Oumuamua firmly within the realm of natural phenomena. They were scientists bending over backward, pushing the boundaries of known astrophysics to explain a truly unprecedented object. They were trying to find an explanation for the silent engine, without resorting to the truly extraordinary. Because the alternative, the truly paradigm-shifting idea, was almost too audacious to consider. You see, for centuries, humanity has scanned the skies, listening for a whisper, a signal, a sign that we are not alone. We've imagined what such a message might look like: a radio wave, a laser pulse, a beacon of light. But what if a message in a bottle, cast into the cosmic ocean, doesn't look like a deliberate communication at all? What if it looks like a silent, tumbling shard of rock and metal, sent on a journey of millions of years, briefly passing our firelight before disappearing back into the dark? What if it looks exactly like Oumuamua? The silent comet had spoken, not with a roar, but with a whisper so subtle, so profoundly unexplainable by conventional means, that it demanded an entirely new kind of listening. And some, like Harvard's Avi Loeb, were ready to listen to the whisper, no matter how radical the implications. But before we dive headfirst into the truly extraordinary, into the realm of the artificial, it's crucial to understand the equally brilliant, equally imaginative efforts of another tribe of scientists. This group, armed with the bedrock principles of astrophysics and planetary science, sought to explain Oumuamua not as a message, but as a marvel of nature. They looked at the same bewildering data, felt the same intellectual tremor, and asked, what if it's something we haven't seen before, but is still entirely natural? What if this isn't an alien technology, but a shard of a distant world, a cosmic iceberg carved from an exoplanet, sent on an unimaginable journey across the interstellar ocean? Imagine for a moment a world far beyond our solar system, perhaps circling a star millions of light years away. Picture a place profoundly cold, a distant frozen dwarf planet, not unlike our own Pluto, blanketed in thick layers of nitrogen ice. Now, imagine a cataclysmic event, a violent collision with another celestial body, or perhaps the chaotic gravitational dance of a young forming planetary system. From this cosmic upheaval, a piece breaks off, a fragment, perhaps oblong, perhaps irregular, but imbued with the raw material of its home world, solid nitrogen. This is the origin story of Oumuamua, as imagined by astrophysicists Alan Jackson and Stephen Dish from Arizona State University. This wasn't just a whimsical guess. It was a scientifically rigorous hypothesis, an elegant attempt to reconcile all of Oumuamua's bizarre traits with known physics and chemistry. Their nitrogen iceberg theory quickly became the leading natural explanation, offering a compelling narrative for our first interstellar visitor. The most profound paradox, the one that kept astronomers up at night, was Oumuamua's non-gravitational acceleration. You see, when an object like a comet approaches the sun, the heat causes its surface ices to sublimate, turn directly from solid to gas. This outgassing creates a jet-like effect, pushing the comet and forming the characteristic glowing cloud, or coma, and tail that we associate with these celestial wanderers. But Oumuamua had no visible coma, no discernible tail, despite accelerating away from the sun, as if gently pushed by an unseen force. This deviation from a purely gravity-based trajectory was subtle but significant, detected at a remarkable 30th significance, resulting in a total velocity change of about 17 meters per second. It was like watching a sailboat glide across the water, with no wind in its sails, no motor churning the water, yet still picking up speed. Here's where the nitrogen iceberg theory delivers its aha moment, a moment of profound scientific elegance. What if the exhaust fumes were simply invisible? Nitrogen ice, N22, is abundant on bodies like Pluto and Neptune's moon Triton, making it a plausible component for an exoplanetary fragment. When solid nitrogen sublimates, it turns into gaseous nitrogen. And here's the kicker. Gaseous nitrogen, unlike water vapor or carbon dioxide, is nearly transparent to our telescopes, at the wavelengths astronomers were using to look for a coma. So, if Oumuamua was indeed a chunk of nitrogen ice, it could have been outgassing furiously, propelling itself forward, without leaving any visible trace for us to detect. The cosmic sailboat did have a propulsion system. We just couldn't see the exhaust. This single insight solved the central riddle, transforming Oumuamua from an inexplicable anomaly into a comprehensible, albeit extraordinary, natural phenomenon. But the nitrogen iceberg theory didn't stop there. It also offered compelling explanations for Oumuamua's other peculiar characteristics. Remember that extreme, bizarre shape? The light curve data, the dramatic periodic change in brightness by a factor of 10, suggested an object that was perhaps 10 times longer than it was wide, initially envisioned as a cigar. Later analyses even opened the door to a thin pancake-like or oblate spheroid shape. How could a natural object acquire such an unprecedented form? Jackson and Dish proposed that a nitrogen iceberg traveling through interstellar space for millions of years, would be constantly bombarded by cosmic rays. This relentless erosion, combined with the gradual sublimation of its surface due to faint interstellar heating, would cause the object to slowly wear away. Over such immense timescales, softer or more exposed parts would erode faster, naturally sculpting the object into an increasingly flattened or elongated shape, like a bar of soap slowly dissolving in water, until it became the extreme pancake or cigar we observed. Imagine that original chunk, irregular and perhaps chunky, being whittled down over eons into its final streamlined or flattened form by the very forces of the cosmos. Then, there was the reddish color, similar to many objects found in the outer solar system. This, too, found an explanation within the nitrogen iceberg framework. The same cosmic ray bombardment that shaped the object could also chemically alter its surface, creating a reddish, tholin-like crust. Complex organic molecules, often found on distant icy bodies. This space tan would protect the deeper nitrogen ice, allowing the object to survive its long interstellar voyage. And the chaotic tumbling? Oumuamua wasn't spinning smoothly like a perfectly balanced top. It was observed to be chaotically tumbling on a non-principal axis rotation. This erratic motion could also be a consequence of the uneven sublimation. As different parts of the irregularly shaped nitrogen iceberg sublimated at varying rates, they would exert slightly different forces, causing the object to wobble and tumble in its strange, uncontrolled dance. The journey of such an object is itself awe-inspiring. Picture this: a fragment, perhaps 45 by 44 by 75 meters, though early estimates were as large as 400 meters long. It breaks free from its exo-Pluto home and embarks on a silent, solitary voyage across the unimaginable distances between star systems. For hundreds of millions of years, this cosmic iceberg drifts through the cold, dark void, a tiny, resilient shard carrying the history of a distant birth. Then, by chance, it enters our solar system with a hyperbolic excess velocity of 26.33 kilometers per second, about 59,000 km/h. It slingshots around our sun, reaching a blistering maximum speed of 87.71 kilometers per second, 196 km/h. At its closest approach, closer than Mercury's orbit, on September 9, 2017. It makes a relatively close pass by Earth on October 14, 2017, at about 24 million kilometers. And then, just as quickly as it appeared, it's gone, accelerating away, its invisible nitrogen breath propelling it back into the interstellar night, observed for only about 80 days after its discovery before becoming too faint to see. It's important to note that the nitrogen iceberg theory wasn't the only natural explanation proposed. Earlier, a hypothesis suggesting Oumuamua was a hydrogen iceberg was put forth by Daryl Seligman and Gregory Laughlin. This theory also sought to explain the invisible outgassing, as molecular hydrogen gas would also be transparent. However, later scientific analysis, including work by Avi Loeb, argued that a hydrogen iceberg would be far too fragile to survive the harsh environment of interstellar space for millions of years. Interstellar radiation would cause it to evaporate long before it ever reached our solar system, making it an unlikely candidate. The nitrogen iceberg, with its greater resilience, thus presented a more robust and scientifically plausible natural explanation for Oumuamua's enduring mysteries. The beauty of the nitrogen iceberg theory lies in its ability to take seemingly inexplicable anomalies and resolve them within the framework of conventional astrophysics. It doesn't require new physics or exotic materials. It simply asks us to consider the cosmic equivalent of a very specific, very rare, and very long-traveled snowflake. It posits that Oumuamua was a representative of a new class of interstellar objects, fragments of distant icy exoplanets constantly being ejected into the galactic void. The universe, in its infinite creativity, simply presented us with a type of object we hadn't yet had the chance to categorize. This perspective offers a profound sense of continuity, connecting Oumuamua not to an unknown intelligence, but to the vast dynamic processes of planetary formation and destruction happening across the galaxy. It transforms our first interstellar visitor into a silent ambassador from a myriad of distant worlds, a frozen relic carrying the story of stellar nurseries and collapsing protoplanetary disks, arriving not with a message, but with the raw, untamed wonder of the cosmos itself. And yet, even with such an elegant and compelling natural explanation, the debate was far from settled. For some, the sheer confluence of Oumuamua's anomalies, the extreme shape, the lack of coma, the non-gravitational acceleration, felt like too many coincidences for a purely natural explanation to fully satisfy. While the nitrogen iceberg theory was a powerful contender, another tribe of scientists, led by the charismatic and provocative Loeb, felt compelled to consider something truly unprecedented. They were ready to entertain a possibility that challenged our deepest assumptions about our place in the universe, asking if Oumuamua might not be a shard of a distant world, but a deliberate artifact, a piece of technology from a civilization far, far away. And yet, even with such an elegant and compelling natural explanation, the debate was far from settled. For some, the sheer confluence of Oumuamua's anomalies, the extreme shape, the lack of coma, the non-gravitational acceleration, felt like too many coincidences for a purely natural explanation to fully satisfy. While the nitrogen iceberg theory was a powerful contender, another tribe of scientists, led by the charismatic and provocative Loeb, felt compelled to consider something truly unprecedented. They were ready to entertain a possibility that challenged our deepest assumptions about our place in the universe, asking if Oumuamua might not be a shard of a distant world, but a deliberate artifact, a piece of technology from a civilization far, far away. What does a message in a bottle look like when the ocean is the space between stars? Does it look like a radio wave, a deliberate ping across the void? Or does it look like a silent, tumbling shard of rock and metal, sent on a journey of millions of years, briefly passing our firelight before disappearing back into the dark? In 2017, we may have seen one, and we let it get away. For Professor Loeb, chair of Harvard's astronomy department, the natural explanations, while ingenious, felt like trying to fit a square peg into a round hole. Loeb is a figure who ignites strong opinions in the scientific community. Brilliant, articulate, and fiercely independent, he has a reputation for challenging scientific dogma, for daring to ask questions that others might deem too provocative or even outlandish. He's been known to draw comparisons to Galileo, not in a boastful way, but to highlight the often uncomfortable path of true scientific progress, where established views are sometimes upended by unexpected evidence. His willingness to entertain extraordinary possibilities, even when it puts him at odds with the mainstream, makes him a compelling figure in this unfolding mystery. From Loeb's perspective, the non-gravitational acceleration was the most critical piece of the puzzle. Remember, this was the slight, persistent push Oumuamua experienced as it sped away from the Sun, a velocity change of about 17 meters per second, detected with an astounding 30 sigma significance. For most comets, that push comes from outgassing, gases boiling off the icy surface, creating tiny rocket-like thrusts. But Oumuamua had no visible tail, no coma, no telltale signs of gas or dust. The nitrogen iceberg theory offered an elegant solution, suggesting invisible nitrogen gas, But what if there was another, even more radical explanation? Imagine for a moment a ship that sails not on water, but on light. It's not science fiction anymore. Here on Earth, we're already developing light sails, ultra-thin, highly reflective sheets designed to be propelled through space by the sheer pressure of photons, tiny particles of light. Projects like Breakthrough Starshot envision sending tiny probes to other star systems using powerful lasers here on Earth to push them to incredible speeds. The principle is simple. Light, even though it has no mass, carries momentum. When photons bounce off a reflective surface, they impart a tiny push. In the vacuum of space, over vast distances, that tiny push can accelerate an object to incredible velocities without a single drop of fuel. Now, let's look at Oumuamua through this lens. What if its non-gravitational acceleration wasn't from invisible gas, but from the gentle, persistent pressure of our own sun's light? Our sun, a star, emits a constant stream of photons. If Oumuamua was an incredibly thin, wide object, like a sail, it would naturally be pushed by solar radiation pressure. No outgassing needed, no visible coma required, just a silent, gentle shove from the light itself. And this brings us to the aha moment of Loeb's hypothesis, the core idea that suddenly made Oumuamua's strangeness coalesce into something coherent. Remember the light curve data, the dramatic periodic change in brightness by a factor of 10 that told us Oumuamua had an extreme shape? Initial interpretations often leaned towards a cigar-like object, perhaps 10 times longer than it was wide. But later analysis of that same light curve data, particularly when considering the potential for a very thin object, opened up another possibility. A flat pancake or oblate spheroid shape could also be consistent with the observations. Think about it. What shape is ideal for a light sail? Not a cigar, not a sphere. It's something incredibly thin and wide, maximizing the surface area exposed to the light while minimizing mass. A pancake shape, a razor-thin wafer, would be perfectly suited to catch the sun's photons and be pushed along. If Oumuamua was indeed a thin, flat object, perhaps only tens of meters across, but just millimeters thick, a cosmic frisbee, if you will, then the slight non-gravitational acceleration it experienced would be precisely what you'd expect from a light sail being pushed by solar radiation. Suddenly, the lack of a cometary tail, which had baffled astronomers, became a feature, not a bug. A light sail doesn't need to burn fuel or shed material to move. It just needs light. The object's reddish color, similar to many objects in the outer solar system, could be a result of its journey through interstellar space, accumulating a protective layer from cosmic rays over millions of years. Or perhaps it was a deliberate coating designed to endure the harsh vacuum and its chaotic tumbling. A derelict light sail, no longer actively steered, might well tumble end over end, spinning irregularly as it coasts through the void. This is where the narrative tension truly lies. Two tribes, looking at the same profound anomalies, arriving at wildly different, yet scientifically argued conclusions. On one side, brilliant minds, stretching the boundaries of natural phenomena to explain the unprecedented. On the other, Loeb, asking if the simplest explanation for something behaving like technology is that it is technology. The philosophical implications of Loeb's hypothesis are staggering. If Oumuamua was an artificial light sail, it wouldn't necessarily mean it was an active probe, beaming messages back to its creators. It could be something far more poignant. A piece of space junk, a discarded fragment of a much larger craft, or perhaps a dormant, passive buoy, sent out by a civilization millions of years ago, now just drifting silently through the cosmos. The name Oumuamua, Hawaiian for a messenger from afar, arriving first, or scout, would take on an entirely new, almost prophetic meaning. Consider the human story of this debate. Loeb's ideas have been met with significant skepticism, even derision, from some quarters of the scientific community. The standard scientific approach rightly demands extraordinary evidence for extraordinary claims. The natural origin camp argues that we should always exhaust all natural explanations before invoking the supernatural or the extraterrestrial. To them, suggesting alien technology crosses a line into sensationalism and unscientific speculation. But Loeb counters that dismissing a hypothesis solely because it's extraordinary is itself unscientific, especially when the natural explanations require so many unique, unprecedented conditions to align. He firmly believes that extraordinary claims require extraordinary evidence, but also extraordinary conservatism requires extraordinary evidence. The tragedy, as Loeb sees it, is that we had a chance, however fleeting, to investigate this potential message in a bottle, and we let it slip away. Discovered on October 19, 2017, Oumuamua had already passed its closest point to the Sun on September 9th and was hurtling out of our solar system. Astronomers had only about 80 days to observe it before it became too faint for even the most powerful telescopes to see. Imagine the frantic scramble, the global astronomical community turning every available eye to the sky. The Very Large Telescope, Gemini South, Keck 2, Hubble, Spitzer, all racing against a cosmic clock. But it wasn't enough. We had a fleeting glimpse, a cosmic hello, and then it was gone, swallowed by the interstellar void, heading towards the Pegasus constellation at a staggering 26.33 kilometers per second. The comparison to 2I Borisov, the second interstellar object discovered in 2019, only amplified Oumuamua's peculiarity. Borisov behaved like a textbook comet, with a clear coma and tail, its non-gravitational acceleration easily explained by outgassing. Borisov was a natural wonder. Oumuamua remained an enigma, its every attribute challenging our conventional understanding. So, here we stand, at a crossroads of scientific thought. Was Oumuamua a fragment of an exo-Pluto, a cosmic iceberg of nitrogen, tumbling silently through the darkness? Or was it a silent sentinel, a piece of advanced technology, sailing on the light of distant stars, briefly illuminated by our own sun, before continuing its lonely journey? The data, ambiguous yet tantalizing, allows for both possibilities, pushing the boundaries of our imagination and our scientific models. The implications of either answer are profound. If it was natural, it forces us to rethink the composition of planets in other star systems and the processes that scatter their fragments across the galaxy. If it was artificial, it fundamentally changes our understanding of our place in the universe, providing the first tangible, if indirect, evidence of intelligent life beyond Earth. It's a question that continues to echo through the halls of academia, inspiring new research, new debates, and new missions. We missed our chance to greet our first known interstellar visitor, but the experience has served as a cosmic wake-up call, spurring the development of new survey telescopes like the Vera C. Rubin Observatory, which are expected to detect interstellar objects more frequently, perhaps once a year. We are preparing for the next one, too, hoping that when the next messenger arrives, we'll be ready to not just observe it, but perhaps finally, to truly understand it. What will the next message in a bottle look like? And will we be prepared to read it? What will the next message in a bottle look like? And will we be prepared to read it? That question lingers, doesn't it? It hangs in the silent, star-dusted air, a testament to the profound, unsettling encounter we had just a few short years ago. Because while Oumuamua has long since vanished back into the cosmic ocean, The debate it ignited rages on, fiercely, passionately, in the minds of scientists across the globe. It's a debate that touches on everything we thought we knew about the universe and our place within it. Imagine, if you will, a cosmic courtroom. The stakes couldn't be higher. Nothing less than our understanding of reality, of life beyond the earth, hangs in the balance. Before us, the jury, that's you by the way, is the evidence, sparse and enigmatic, painstakingly gathered from the brief, fleeting visit of Oumuamua. And on opposite sides, two brilliant, impassioned legal teams, each presenting their case for what this bewildering object truly was. No easy answers here, only profound elegance clashing with significant, unresolved problems. It's the razor's edge of scientific discovery, laid bare. On one side, we have the prosecution, if you will, arguing for a purely natural explanation. Their case rests on the immense, often unpredictable ingenuity of the universe itself. They remind us that for every strange phenomenon, there is usually, eventually, a natural answer, even if it pushes the boundaries of our current knowledge. Their challenge is immense, to explain all of Oumuamua's bizarre characteristics using only the known laws of physics and the material components of the cosmos. The first piece of evidence they must contend with, the one that truly sets Oumuamua apart, is its non-gravitational acceleration. Think about it. This object sped up as it moved away from our sun, as if gently pushed by an unseen hand. Now, comets do this all the time. As they approach the sun, their icy surfaces heat up, releasing gas and dust, a visible coma and tail, and that outgassing acts like tiny thrusters, nudging the comet off its purely gravitational path. But Oumuamua had no visible coma. None. Not a whisper of gas, not a speck of dust, even when powerful telescopes like the Hubble and Spitzer space telescopes tried to find it. It was, to all appearances, a silent, accelerating ghost. This anomaly, this lack of a visible exhaust plume, became the foundational puzzle, the central riddle that baffled astronomers. The deviation from a purely gravity-based trajectory was subtle, but it was there, detected with a statistical significance of 30s, summing to a velocity change of about 17 meters per second. That's like a car, slowly but steadily accelerating without its engine on, or its exhaust pipe spewing fumes. The natural origin camp also had to explain its utterly unique shape. The way Oumuamua's brightness varied so dramatically, by a factor of 10, told astronomers it wasn't round, or even potato-shaped like most asteroids. Instead, it was extremely elongated, perhaps 10 times longer than it was wide. Initial estimates suggested a cigar-like object, but later analysis even opened the door to a flat, pancake, or oblate spheroid shape. Either way, it was unlike any asteroid or comet we had ever seen in our own solar system. And it wasn't spinning smoothly. It was tumbling chaotically, a non-principal axis rotation, adding another layer of strangeness to its profile. So, how do you explain an object that's shaped like a cosmic plank, accelerates without a visible engine, and has traveled millions of years through the cold vacuum of space? One of the earliest attempts to provide a natural explanation came from Darrell Seligman and Gregory Laughlin, who proposed the hydrogen iceberg theory. Their idea was elegantly simple. What if Oumuamua was made primarily of solid molecular hydrogen? If it were, then as it approached the sun, that hydrogen would sublimate, turn directly from a solid into a gas, providing the necessary thrust for its non-gravitational acceleration. Crucially, hydrogen gas is virtually invisible to our telescopes. No visible coma, problem solved. It's a neat solution, right? A silent, accelerating comet, fueled by the most abundant element in the universe. But This theory faced significant challenges. Scientists, including Avi Loeb, later argued that a hydrogen iceberg, even a massive one, simply wouldn't survive the millions of years of interstellar travel. Cosmic rays and ultraviolet radiation would erode it away long before it ever reached our solar system. The extreme cold of space is one thing, but the constant bombardment of high-energy particles would be like a slow, relentless sandblasting, turning a hydrogen iceberg into nothing. This led to another compelling natural theory, one that has gained considerable traction: the nitrogen iceberg theory, put forth by astrophysicists Alan Jackson and Stephen Disch. Their hypothesis posits that Oumuamua was a fragment of nitrogen ice chipped off a Pluto-like exoplanet. Imagine a distant, frozen world, far beyond our solar system, perhaps shattered in some cosmic collision. A piece of its nitrogen-rich surface, blasted free, begins a journey across the galaxy. Like hydrogen, solid nitrogen would sublimate as it neared the sun, providing the non-gravitational push without a visible coma. Nitrogen gas, too, is incredibly difficult to detect with our current telescopes, especially from a fast-moving, receding object. This theory offers some powerful advantages in our cosmic courtroom. First, it elegantly explains the lack of a visible coma. Second, it accounts for the object's reddish color, which is similar to many objects found in the outer solar system, suggesting it was composed of rock and possibly metals and had been exposed to cosmic rays for millions of years. These Pluto-like objects, with their nitrogen ice surfaces, would naturally develop a reddish hue from cosmic ray bombardment over eons. Third, and perhaps most ingeniously, the nitrogen iceberg theory can explain Oumuamua's extreme flat shape. As a nitrogen iceberg travels through interstellar space, it would slowly erode, with its edges and corners wearing away faster than its flatter surfaces, eventually shaping it into an oblate spheroid, like a cosmic pancake, rather than a cigar. This natural erosion process, over millions of years, could sculpt exactly the kind of bizarre, thin object implied by the light curve data. Some models based on this composition suggest dimensions of approximately 45 by 44 by 7.5 meters, a remarkably flat, thin shard. It's a testament to the universe's own sculptural power. The Natural Origin Camp also points to the discovery of 2I Borisov in 2019, the second confirmed interstellar object. Borisov, by contrast, behaved exactly like a typical comet, with a bright, visible coma and tail. This comparison, they argue, highlights just how anomalous Oumuamua's characteristics were, but also reinforces the idea that interstellar objects can be natural. Borisov was a normal interstellar comet. Oumuamua was the strange exception, requiring a more exotic, yet still natural explanation. So, the naturalists present a compelling case. They argue that Oumuamua, though strange, is ultimately a testament to the vast diversity of natural objects found across the galaxy. It pushes the boundaries of what we expect, yes, but it doesn't break them. It forces us to rethink the composition of planets in other star systems and the processes that scatter their fragments across the galaxy. We missed our chance to greet our first known interstellar visitor, but the experience has served as a cosmic wake-up call, spurring the development of new survey telescopes like the Vera C. Rubin Observatory, which are expected to detect interstellar objects more frequently, perhaps once a year. We are preparing for the next one, hoping that when the next messenger arrives, we'll be ready to not just observe it, but perhaps finally, to truly understand it. Now let's turn our attention to the other side of the courtroom, to the defense, as it were. Their case is built on the premise that the anomalies surrounding Oumuamua are not just strange, but too strange for any known or even theorized natural explanation. They argue that the universe's ingenuity, while vast, still operates within certain physical constraints, and Oumuamua, they contend, seems to defy those constraints. Leading this charge is Dr. Avi Loeb, a theoretical physicist at Harvard University. He is a compelling, often controversial figure whose willingness to challenge scientific dogma has made him a lightning rod in the astronomical community. Dr. Loeb, in his arguments, often evokes figures like Galileo, suggesting that sometimes extraordinary claims are necessary to advance our understanding when existing paradigms fail to explain the evidence. He is the intellectual protagonist of this cosmic drama, and his willingness to risk his reputation for a bold idea is, as our strategic analysis noted, pure narrative gold. Dr. Loeb and his colleagues argue that when you stack up all of Oumuamua's bizarre properties, its extreme shape, its lack of a coma, and especially its non-gravitational acceleration, the simplest, most elegant explanation isn't natural at all. Instead, they propose that Oumuamua was an artificial object, a piece of technology, perhaps a light sail propelled by radiation pressure. Let's break down his argument. First, the non-gravitational acceleration. If Oumuamua was a light sail, a very thin, broad object, designed to be pushed by starlight, then as it passed close to our sun, the intense solar radiation pressure would naturally provide that gentle, invisible push. No need for outgassing. No need for an active propulsion system. It's a passive, elegant way to travel through the cosmos. The object entered our solar system with a hyperbolic excess velocity of 26.33 km/s, about 59,000 km/h, and reached a maximum speed of 87.71 km/s, 186,000 km/h, at perihelion. This trajectory, and its subtle deviation, is precisely what a light sail would experience. Second, the extreme shape. A light sail, by its very nature, would be incredibly thin and broad to maximize the surface area exposed to radiation pressure. This would naturally lead to the extreme aspect ratio, the cigar or pancake shape, implied by Oumuamua's dramatic light curve. If it were a very thin, flat object, like a solar sail, its perceived brightness would change dramatically as it tumbled, appearing bright when viewed face-on, and much dimmer when seen edge-on. This fits the observed tenfold variation in brightness perfectly. Third, the lack of a coma. If it's a light sail, it's not made of ice that sublimates. It's a solid, engineered structure. No ice, no outgassing, no visible coma. The silence of Oumuamua, its perfectly clean passage through our solar system, is not a problem for the artificial hypothesis. It's a feature. Fourth, its chaotic tumbling. A light sail, even a damaged or derelict one, might tumble erratically, especially if it's no longer under active control, or if it's been damaged by interstellar dust and radiation over millions of years. This chaotic rotation, rather than a smooth spin, aligns with the idea of an object that has been adrift for a very long time. Dr. Loeb also points to the sheer statistics. While the existence of interstellar objects had been theorized for decades, none had ever been concretely identified until Oumuamua. Its discovery on October 19, 2017, by Robert Warwick, using the Pan-STARRS 1 telescope, was a momentous occasion. But the fact that the first one we ever saw had such profoundly anomalous properties, unlike anything we'd previously imagined for a natural object, stretches the bounds of coincidence. He argues, why would the very first interstellar visitor we detect be so utterly unique, so perplexing, if it were just a random chunk of rock or ice? It was found 40 days after its closest approach to the sun, and was already hurtling away, creating an immediate, frantic race to observe it. This limited observation window, only about 80 days before it became too faint, meant we couldn't get definitive answers. But the data we did gather, Dr. Loeb contends, points away from the mundane. The implications of Dr. Loeb's hypothesis are, of course, staggering. If Oumuamua was indeed an artificial object, a message in a bottle from another civilization, it would be the most profound discovery in human history. It would mean we are not alone, and that advanced intelligence exists, or at least once existed, somewhere out there in the vast cosmos. It also means we missed our chance to study it up close. That tragedy, the emotional and philosophical depth of letting our first known visitors slip away, unexamined, is a powerful undercurrent to this entire debate. So you, the jury, have heard both sides. On one hand, the naturalists, with their elegant theories of exotic icebergs, chipped off distant exoplanets, eroding into bizarre shapes and silently outgassing. It's a compelling narrative of cosmic geology and physics, pushing the boundaries of our understanding of cometary bodies. The hydrogen iceberg theory, while challenged on survivability, offered a simple solution to the invisible outgassing. The nitrogen iceberg theory, championed by Jackson and Dish, provides a more robust explanation, accounting for the shape, color, and acceleration through a plausible, albeit still novel, natural process. On the other hand, Dr. Loeb and his proponents argue that the collective anomalies are simply too much for any natural explanation. They present the case for an artificial origin, a light sail, a piece of alien technology, silently traversing the interstellar void. This theory elegantly explains the non-gravitational acceleration, the extreme shape, and the lack of a coma, all without recourse to speculative, hard-to-prove icy compositions. It offers a solution that, while extraordinary, is remarkably simple in its mechanics. But let's be honest, neither case is airtight. The natural theories, while elegant, require very specific, almost perfect, conditions for these exotic icebergs to form, survive, and then exhibit all of Oumuamua's unique characteristics. Proving the existence of such objects, or observing molecular hydrogen or nitrogen outgassing from light years away, remains incredibly difficult. The universe is vast, and our observational tools are limited. We have no definitive, direct evidence of these specific types of comets. It forces us to stretch our understanding of what a comet can be. And the artificial theory, while captivating, suffers from the age-old problem. Extraordinary claims require extraordinary evidence. We have no definitive images, no direct confirmation that it was engineered. The evidence is indirect, inferential. While the properties are consistent with a light sail, consistency is not proof. The Occam's razor principle, which suggests the simplest explanation is usually the best, often favors natural explanations over artificial ones, unless the natural explanations become overwhelmingly complex or contradictory. This is the aha moment of our cosmic trial. There is no easy answer. Both theories have a profound elegance to them, a beauty in their ability to explain the data. But both also carry significant unresolved problems. We are left on the razor's edge of scientific discovery, where the data itself is ambiguous enough to support wildly different yet plausible conclusions. The truth about Oumuamua remains elusive, lost in the vastness of space and time. The object named Oumuamua, Hawaiian for a messenger from afar, arriving first, or scout, chosen by the Pan Star's discovery team, fulfilled its name perfectly. It was a scout not just for itself, but for the profound questions it would force us to ask. It challenged our assumptions, pushed the boundaries of our scientific imagination, and split the astronomical community into two passionate tribes. So, As you consider the evidence, what do you believe? Was Oumuamua a marvel of cosmic geology, a shard of a shattered exo-Pluto, an exotic iceberg silently melting in our sun's embrace? Or was it something far more profound, a silent, tumbling message in a bottle, sent on a journey of millions of years, briefly passing our firelight before disappearing back into the dark? The debate continues, the mystery endures, and we, humanity, are left to ponder the silent, accelerating ghost that slipped through our fingers, reminding us that the universe holds secrets far stranger than we can often imagine. The only certainty is that the search for answers, the clash of brilliant minds, will continue until the next messenger arrives. And hopefully this time, we'll be ready. The universe, as we've come to understand it, is a vast, echoing place. For centuries we gazed up, wondering if we were alone, if any other cosmic traveler might ever cross our path. Then, in 2017, Oumuamua arrived, a silent, accelerating ghost that shattered our assumptions and left us reeling with profound questions. It was the first confirmed interstellar object ever detected passing through our solar system, and for 2 years, it remained a singular enigma, a one-of-a-kind visitor that seemed to defy every explanation we could throw at it. But then, in 2019, a second visitor came calling, and its arrival, paradoxically, only made Oumuamua seem even stranger. Imagine you're a local, living in a quiet, secluded town. One day, a tourist arrives, unlike anyone you've ever seen. They speak a language you don't recognize, wear clothes that defy local fashion, and their mannerisms are utterly baffling. You spend weeks trying to figure them out, debating amongst yourselves. Are they an eccentric human, a lost soul, or perhaps something else? Just as you're about to give up, another tourist appears from the same distant country. This one, however, is perfectly understandable. They speak a common tongue. Their clothes are familiar, and they act exactly as you'd expect a visitor to act. What does this do to your perception of the first tourist? Suddenly, the initial mystery deepens. The first one wasn't just different. They were profoundly, uniquely strange. This is precisely the aha moment that 2I Borisov delivered to the scientific community. Oumuamua was our first tourist, the bizarre, inexplicable stranger. Borisov was our second, the normal cousin, who arrived 2 years later, and in its very normality, solidified Oumuamua's status as an unparalleled enigma. Let's rewind for a moment to that frantic scramble in late 2017, when Robert Warwick, at the University of Hawaii's Pan-STARRS 1 telescope, first spotted Oumuamua in the data on October 19, 2017. It was already 40 days past its closest approach to the sun. It was a ghost in the making, already hurtling away, making its escape from our solar system. The race was on, a global, desperate sprint to gather any scrap of information before it vanished forever. Every available telescope, from the Very Large Telescope to Hubble and Spitzer, swiveled to catch a glimpse. Oumuamua was a cosmic riddle wrapped in a paradox. Its orbital eccentricity was a staggering 1.3, the highest ever observed at the time, screaming its unbound interstellar trajectory. It entered our system screaming, with a hyperbolic excess velocity of 26.33 km/s, about 59,000 km. At its closest point to the Sun, its perihelion, it hit a mind-bending 87.71 km/s, or 196,000 km/s. You see, the most profound anomaly was its non-gravitational acceleration. As it sped away from the Sun, it wasn't just following the predictable tug of our star's gravity. It was pushing away, ever so slightly, as if gently nudged by an unseen force. For any comet we'd ever observed, this push is easily explained. As the sun heats the comet's icy surface, gases and dust erupt, creating a beautiful glowing coma and a characteristic tail, acting like tiny thrusters. But Oumuamua had no visible coma, no tail, no puff of gas or dust. It was just a silent, tumbling shard, accelerating without any visible means of propulsion. Then, there was its shape. Its brightness varied dramatically as it tumbled, by a factor of 10. This wasn't a gentle wobble. It suggested an extreme, highly elongated form, perhaps 10 times longer than it was wide. Imagine a cosmic cigar, or later, a flat, pancake-like object spinning chaotically on a non-principal axis, like a lost child turning cartwheels in the void. Nothing we knew, no asteroid, no comet, looked like that. It even had a reddish color, like so many ancient objects found in the outer solar system, hinting at eons of exposure to cosmic rays. For 2 years, the scientific community wrestled with these anomalies. Hypotheses were put forth, some brilliant, some bordering on the fantastical. Could it be a hydrogen iceberg, silently outgassing invisible hydrogen, explaining the acceleration without a visible tail? Or perhaps a nitrogen iceberg, chipped off, a Pluto-like exoplanet, slowly eroding and releasing invisible nitrogen gas. But each explanation came with its own set of challenges and questions, leaving the mystery largely intact. The debate raged. The two tribes of astronomers, those favoring natural explanations no matter how exotic, and those like Harvard's Avi Loeb, daring to consider the artificial, dug in their heels. Then came Borisov. On August 30th, 2019, an amateur astronomer in Crimea, Gennady Borisov, spotted something new, a fuzzy smudge against the stars. Within weeks, professional observatories confirmed it. This was another interstellar visitor, the second ever detected, and it was officially designated 2I Borisov. But as the data streamed in, a profound realization began to dawn. Unlike Oumuamua, Borisov behaved exactly as a comet should. It was textbook. It had a glorious, unmistakable coma, a glowing halo of gas and dust, and a distinctive, beautiful tail stretching millions of miles into space. This visible outgassing perfectly explained its non-gravitational acceleration, its trajectory, its speed, its composition. Everything fit the established models of what an interstellar comet, a shard of ice and rock, flung from another star system, should look like. It was a cosmic sigh of relief, a familiar face in the bewildering crowd. And that's when the true peculiarity of Oumuamua snapped into sharp focus. Borisov wasn't just a second interstellar object. It was the ultimate control experiment. Think about it. Before Borisov, you could argue that Oumuamua was simply the first of its kind, and we just hadn't encountered a natural interstellar object before. Maybe they all looked like that. Maybe they were all cigar-shaped, silently accelerating, devoid of a coma. But then Borisov arrived, the very embodiment of a normal interstellar comet, and it blew that idea out of the water. The sheer normality of Borisov didn't resolve the Oumuamua mystery. It amplified it. It was as if the universe sent us two messages, one in plain language, clear and unambiguous, and the other, a coded enigma, utterly unlike anything we had expected. Borisov's very existence, its predictable cometary splendor, served as a powerful unspoken argument for Oumuamua's truly anomalous nature. Harvard's Avi Loeb, the most prominent proponent of the artificial origin hypothesis, found his arguments gaining new weight. He continued to champion the idea that Oumuamua's properties were consistent with a light sail, a thin, wide object propelled by solar radiation, designed to traverse the vast emptiness between stars. Such an object would naturally be thin, could tumble chaotically, and would experience non-gravitational acceleration from the sun's radiation pressure without any need for outgassing. The arrival of Borisov meant that scientists could no longer simply shrug and say, well, that's just what interstellar objects are like. No. Now we knew what at least one interstellar object was like. And Oumuamua was nothing like it. This wasn't a matter of subtle differences. It was a chasm. One was clearly a comet, a natural wonder of interstellar ice and dust. The other remained a profound question mark. The scientific debate, already fierce, only intensified. The unnatural origin camp was now tasked with explaining not just Oumuamua's unique features, but why those features were absent in Borisov. Why did Oumuamua, if natural, defy all cometary norms that Borisov so perfectly embodied? Why was it so much more elongated, so much more silent in its acceleration? The exotic ice theories, like the hydrogen iceberg, faced renewed scrutiny, as the question of their survival, over millions of years of interstellar travel, remained contentious. The lessons from Oumuamua and Borisov are shaping the future of astronomy. The frantic real-time race to observe Oumuamua and the slightly more relaxed but equally vital observations of Borisov have underscored the importance of being ready. Projects like the Vera C. Rubin Observatory, with its unprecedented sky survey capabilities, are expected to detect interstellar objects more frequently, perhaps even once a year. And with that expectation comes the tantalizing possibility of rapid response missions, projects like the Comet Interceptor, designed not just to observe, but to potentially rendezvous with and study these cosmic visitors up close. So, as you stand at the frontier of this incredible mystery, consider the evidence. Oumuamua was a stranger, an anomaly that defied our every expectation. Borisov was its cousin, a familiar face that by its very normalcy highlighted just how profoundly unique Oumuamua truly was. This isn't just a story about two rocks in space. It's a story about what those rocks force us to confront, about ourselves, our place in the universe, and the endless possibilities that lie beyond the stars. The first visitor left us with a haunting question. The second visitor, by its very nature, only made that question echo louder. The first visitor left us with a haunting question. The second visitor, by its very nature, only made that question echo louder. But here's the thing about echoes. They don't just fade into silence. Sometimes they spur us into action. They tell us where to listen, where to look, and how to be ready for the next sound. Imagine for a moment that the universe is an endless ocean, vast and unknowable. Our solar system is a tiny island, a cozy harbor where we've built our firelight. For generations, we peered out at the waves, wondering if there was anything beyond our shores. Then, in 2017, a message in a bottle, silent and strange, drifted briefly into our light. It was Oumuamua. We saw it barely, as it sped past, a fleeting glimpse of something truly alien. We couldn't catch it, couldn't examine it up close. We simply watched it disappear back into the dark. We missed that first bus, but seeing it go by taught us something profound. There is a bus stop. And now, we are building a rocket to catch the next one. This isn't just about looking for more rocks. It's about preparing for the unknown, for the next piece of evidence that could redefine our place in the cosmos. Oumuamua was a wake-up call, a celestial alarm clock that screamed, "You are not alone in this vast ocean, and things are coming." Its extreme cigar-like or pancake shape, its peculiar tumbling, its inexplicable non-gravitational acceleration without a visible coma. Each anomaly was a clue, a data point that pushed us to reconsider what we thought we knew about interstellar objects. We had only about 80 days to track it before it became too faint for even our most powerful telescopes. That limited window of observation highlighted a critical need. We need to be faster, more vigilant, and more prepared. The scientific community, galvanized by Oumuamua's enigmatic flyby, realized that waiting for these interstellar visitors to announce themselves with a casual stroll through our inner solar system simply wouldn't cut it. We needed to actively scan the skies, not just for objects that might hit us, but for those that might tell us where we came from, or perhaps where others are. Enter the Vera C. Rubin Observatory, a monumental undertaking perched high in the Chilean Andes, designed to revolutionize our understanding of the dynamic universe. With its first images having already captured thousands of previously unknown asteroids, including near-Earth objects, Rubin isn't just another telescope. It's a cosmic sentinel. Its legacy survey of space and time, LSST, will be like a tireless eye, scanning the entire southern sky every few nights, creating a real-time time-lapse movies of the universe. This unprecedented depth and cadence mean that the Rubin Observatory is uniquely capable of catching fast, faint objects like Oumuamua or the 3I Atlas, which can easily slip by unnoticed if the sky isn't constantly monitored. The sheer scale of data it will collect is mind-boggling, capturing more than a petabyte of data every night, which will allow astronomers to track even faint and fast-moving bodies with precision. Scientists anticipate that Rubin will dramatically increase our census of solar system objects, potentially quintupling what we currently know. More importantly for our story, the Rubin Observatory is expected to detect interstellar objects with a frequency that would have been unimaginable just a few years ago. While initial estimates varied, some researchers now suggest that the LSST could find anywhere from 0 to 70 asteroidal interstellar objects every year, with other estimates around 0.9, 1.9, or even 5 to 50 ISOs annually. This means we could go from studying 2 known interstellar objects to a population of dozens, providing an invaluable data set to understand how planetary systems form across the Milky Way. Imagine the implications. Instead of a once-in-a-lifetime anomaly, we could be looking at a steady stream of these interstellar travelers. Each one a potential messenger, each one a unique sample of material from another star system, carrying secrets from before our own sun was born. What will they look like? Will they be more Oumuamua-like, defying easy classification, or more Borisov-like, clearly cometary? The Rubin Observatory, with its massive 8.4-meter telescope and a 3.2 gigapixel camera, the largest digital camera ever built for astronomy, will capture these fleeting visitors in exquisite detail, providing crucial early warnings. Its automated alert system, triggering millions of alerts nightly, means that potential interstellar objects will be flagged quickly, giving astronomers the crucial lead time needed for follow-up observations. But detection is only half the battle. What if we could do more than just watch them pass by? What if we could actually meet one? This is where the ESA's Comet Interceptor mission comes into play, a testament to humanity's renewed ambition and ingenuity. Planned for launch in 2029, Comet Interceptor is a mission designed with a truly unique strategy. It will launch without a specific target. Instead, this multi-element spacecraft will journey to the Sun-Earth Lagrange point L2, a stable gravitational parking spot about 2.5 million kilometers from Earth, where it will patiently wait for up to 3 or 4 years for a suitable interstellar object or a pristine long-period comet to be discovered. This waiting game approach is revolutionary. Historically, by the time a dynamically new comet or an interstellar object is discovered, it's often already past its closest approach to the Sun and hurtling away, leaving too little time to design, build, and launch a mission to intercept it. Oumuamua, was a prime example of this too little, too late dilemma. But with observatories like Rubin providing much earlier detection, Comet Interceptor can then be directed to its target. Comet Interceptor isn't just one spacecraft, it's a trio. It comprises a primary platform, which acts as the communications hub, and two smaller sub-spacecraft, one provided by JAXA, the other by ESA. Once a suitable target is identified by ground-based observatories like Rubin, the three spacecraft will travel together. Then, a few weeks or even days before the flyby, they will separate, allowing for simultaneous multi-point observations from different perspectives around the object. Imagine that, three sets of eyes scrutinizing an object that has traveled unimaginable distances from another star system. This multi-point approach will allow scientists to create a detailed 3D profile of the object, characterizing its surface composition, shape, structure, and the composition of its gas coma and plasma environment. If the target happens to be an interstellar interloper, like a future Oumuamua, this mission would offer an unparalleled opportunity to explore how comet-like bodies form and evolve in other star systems. It would allow us to study pristine material, untouched since the dawn of star formation, offering direct insights into the building blocks of other planetary systems. The scientific goals are profound: to understand the formation of habitable environments in the solar system, and to elucidate the universal laws that govern space gases. It will help answer questions like, what does a pristine comet or interstellar object look like up close? And how are pristine comets different from the comets we know? By examining the craters, depressions, surface dust, and rocky composition, and even identifying organic molecules and isotope ratios, Comet Interceptor could shed light on how comets may have contributed to the surprisingly rapid emergence of life on Earth. This is a game changer. We're moving beyond remote speculation, beyond artists' impressions based on tantalizing light curves. We're building the tools to get up close and personal with these cosmic wanderers. It's a collective human effort, a testament to our insatiable curiosity. We've learned from our scramble to observe Oumuamua, which was detected only after it passed its closest point to the Sun and was already on its way out. We won't make that mistake again. We are actively creating a future where we are ready. The philosophical implications are as vast as the cosmos itself. If Oumuamua truly was a message in a bottle, then the next one might not slip away unread. We are developing the capacity to not just observe, but to interact with these objects, to gather the kind of definitive data that could finally settle the debate. Natural phenomenon or extraterrestrial technology. A mission to intercept one of these objects, image its nucleus, and collect basic chemical data would readily resolve between these or other possibilities, and would be truly transformative for both planetary and exoplanetary science. The ultimate answer may not come from endlessly poring over the limited data of the past, but from being ready for the next visitor. We missed the first bus, yes, but its fleeting passage showed us the way. We built the bus stop, the advanced observatories like Rubin, and now we're building the rocket to catch the next one. The Comet Interceptor. This isn't just about catching up. It's about being prepared for a future of discovery that could fundamentally alter our understanding of life, intelligence, and our place in a potentially crowded universe. Now that we know they are coming, are we prepared for what we might find?